let me quickly go through the last week one. Just all right. Can you see my screen now?
Yes, madam.
Okay, thank you. So let's quickly go through what we discussed during the last week. So for the instrumentation part, we discussed what are the classical methods and instrumental methods for the analysis, and we went through both of these methods, and we discussed the main components of instruments and what are the sources and all these things. And also we discussed how the information can be transformed to the data. So we talked about the electrical, non-electrical domains, and how the information transfer between non-electrical and electrical domains, and brief introduction for the detectors, transducers, and sensors. Those things we will be discussed in detail later, and some examples. And also calibration methods available after we perform the instrumental analysis. What are the calibration methods available? So all 4 types of calibration methods. And finally, we discuss about the figures of merit and how we can select a particular instrument based on our requirements. So, or 6 figures of merits. Sensitivity, selectivity, detection limit, all these things. So that's where we stopped. I hope you all work on this question. So is there any problem? Is it good, the question? You can answer this one, right? I think we went through this question as well. Have you tried to answer this question? Fine.
Yes, madam.
Okay, so is there any problem in answering, or all good?
All good, madam.
Okay. Okay, then today we will discuss, let's see. Okay, signals and noise. Okay, so is it visible, the signals and noise part, the presentation? Can you see my screen, signals and noise presentation?
Yes, madam, we can.
All right. Okay, then let's discuss about signals and noise today. And this is one of another most important part that we should learn when we dealing with instrumental data. So whatever the instrument we are using, and then whatever the data we acquire from that instrument, there are always 2 components are there. One is the signal, that is what we are interested in, and also there are some noise associated with the signal. So we will sometimes it is difficult for us to get rid of this noise, but sometimes we can get rid of the noise part. So let's talk about the signals and noise today. Okay, so as I mentioned, one of the two components in an analytical measurement, these signals and noise, these two components are the important components in any analytical measurement. The signal, when we talk about the signal contains all the information that we are interested in. So it has the useful information about the analyte that we need to analyze. But the noise, we don't need any noise. It is some it contains additional information that we are not interested. So when there's noise present, it degrades the accuracy and the precision of our data set. So noise part is signal, we are interested in the signal, but noise, we don't need to have noise part in our let's say spectrum or any data set. And the signals are information, and information is energy. So we convert this energy to useful information as signal. And this figure, you can see the signal. That is the original signal, that if there's no any noise part, the signal should be looks like this. But almost every time in any instrument, noise part is available. Therefore, whatever the result we get will be like this. It will have both signal and noise. So we will not, most of the time, we will not get any clear or good spectra or any signal like what we are expecting. It will be always some messy scan or messy spectrum, right? Therefore, there should be a way to increase the signal. And when we talk about that, it is important to talk about the signal to noise ratio. Right? So when we talk about the signal to noise ratio, that is the mostly used part in the when we talk about the measurement. And in most measurement, noise is constant, and it is not depend on the magnitude of the signal. So noise part, any noise associated with the instrument, it is almost, in most of the cases, it is constant. It is not changing. Therefore, noise is not changed with the signal. So, if we increase the intensity of the signal, if we can increase the intensity of the signal by increasing the quantity that we are measuring. So, if we increase the quantity that we are measuring, we can enhance the intensity of signal. When we enhance the intensity of signal, I told you the noise part is not changing with the magnitude of the signal. Therefore, we can minimize the effect of the noise part. So we can say that this signal and noise has inverse proportionality. So because of that inverse proportionality, it is always better to describe this instrumental performance from the signal to noise ratio rather than describing it in the noise alone, right? And as a general rule, normal rule is when the signal to noise ratio is less than 2 or 3, it is difficult to detect the signal. When the ratio is signal to noise ratio is less than 2, it says 2 or 3, but let's say when the ratio is less than 3, it is difficult or it is impossible to detect a clear signal. So always when we take a measurement from any instrument, the signal to noise ratio should be greater than 3, right? And this is an example. This is an example of a NMR spectrum that is obtained, the spectrum A, the first one. In the first spectrum A, the signal to noise ratio is 4.3. It is higher than 3, but still we cannot see some distinct peaks. It is difficult for us to see distinct peaks in this spectrum, right? Always the noise is higher. But in the same component, in the same sample, when we do the analysis, NMR analysis in the same sample, when we increase the signal to noise ratio to 43, that means 10 times of the spectrum A. When we increase the signal to noise ratio by 10 times, now we can clearly see nice spectral features, right? So this shows us that when we increase the signal to noise ratio, we can take distinct peak for the desired signal. Okay, right. So now we know it is important to have an idea about the noise and the signal. So before we get an idea, we should know what are the possible sources of noise. So if we know the possible sources of noise that any instrument associate with, it is easy for us to troubleshoot, and it is easy for us to get a better spectral data. So let's discuss what are the sources of noises available and associate with the instruments, and also we should talk about how we can enhance the signal to noise ratio, because now I told you that by increasing the signal to noise ratio, we can get good spectrum, better spectrum, but we should know how to enhance the signal to noise ratio. Right. Then first let's discuss what are the sources of noise. Okay, so there are two main sources of noise associated in the instrumental analysis. The first one is the chemical noise, and the second one is instrumental noise. So this instrumental noise, we can divide it into 4 categories: thermal noise, or we call it as Johnson noise, and shot noise, flicker noise, and environmental noise. So this is how these are the main types of noise associated with the instruments, and we will discuss these different types of noise in detail. Right? First thing, chemical noise. What is chemical noise? So the chemical noise, it is the one type of noise that we cannot, that is difficult to control. right? So it arises from uncontrollable variables that affect the chemistry of the system being analyzed. So it happens due to the certain uncontrollable variables which is associated with the our sample, and it affects the chemistry of the sample that we are analyzing. So that is called the chemical noise. Now let's see what are the let's see few examples of this chemical noise. One is the undetected temperature or pressure variation. There can be some temperature or pressure variations in the sample. So if that happens, because it is difficult for us to detect when we are doing some analysis, there might be some temperature or pressure variations associated with the sample during the analysis, but for us it's difficult to detect. So in that case, this variation affects the chemical equilibria and it will change the sample state. So it will change the appearance or whatever the things, it will change the chemical nature of the sample. So if that happens, we will see it as a noise at the end of the analysis. And another example is the fluctuations in relative humidity. So the moisture content can be changed. Even if that happens, there might be some noise associated with the final spectrum. And vibrations of the molecule can happen, so we cannot detect it. In that case also, certain amount of noise will be there. And the light intensity will be changed. Most of the cases when we do UV visible spectral analysis, we are passing the light through the sample, but if there are some photoresponsive material that we are analyzing, then that source light also, that photoresponsive material in the analyte will be react with the light source, and then it may change the structure of the molecule or state, or it will undergo certain chemical changes. In that case also, we will get something else other than the signal. And in many laboratories, we have fumes associated with the several labs. So those fumes will also act as a chemical noise when we take the measurements, right? So those are some examples of the chemical noise. So this chemical noise, it affects the chemistry of the sample, and it is difficult to avoid this chemical noise. And then let's talk about the second type, instrumental noise. Instrumental noise means this instrumental noise associated with each component of an instrument. When we talk about the instrument, it has sources, transducers, it can be input or output transducers, and some signal processing elements, some detectors. All these things are available in the instrument. So with these components, the noise arises because of any thermal or electrical changes in those components. So this instrumental noise is associated with each component of an instrument. When we talk about the instrumental noise, in contrast to chemical noise, we can control this instrumental noise. It can be either physical way or electronic way. For example, we can check if the temperature is increasing in certain parts of the instrument, we can minimize the temperature. So that is one of the way to control the instrumental noise physically. And also electronically means some computer algorithms are available, like software averaging or all these things. We will discuss those two in upcoming slides. And by using those electronic changes, software averaging or filtering or whatever the thing, we can control the instrument noise. Right? So this instrumental, this is how we define the instrumental noise. And as I mentioned earlier, there are 4 types of instrumental noise: thermal noise, shot noise, flicker, and the environmental noise. Then let's discuss in detail of these 4 different types of instrumental noise. First one is the thermal noise. We call it as the Johnson noise also. Both are same, thermal or Johnson noise. This thermal noise arises due to the thermal agitation of electrons or any other charge carrier in the electronics. So electronics means it can be a resistor, capacitor, radiation transducer, or any electrochemical cells, or any other resistive element in the instrument. So when the thermal agitation of electrons or whatever the other charge carrier happens in those different components, thermal noise or Johnson noise arises. And this is what is happening. Because of the thermal agitation, there will be accumulation of the electrons, or therefore charge inhomogeneities will be there. Because of the charge inhomogeneities, voltage of that particular instrument or in that particular component will be fluctuate. It will change. Because of the charge inhomogeneity, voltage fluctuations can happen. Then, because of these voltage fluctuations, it will generate a current, right? When the voltage is changing, the current will also change. It can be and it is a random change. So when the current is changed, the readout device will detect this current. The readout device does not have any ability to isolate signal from the noise. Readout device doesn't know whether it is the important, whether it is wanted thing or unwanted thing. But what is happening, this voltage, the current generated because of the voltage fluctuations will be detected and by the detector, and it will show as the noise in readout device. So that is how the thermal noise happens. And this thermal noise depends on both temperature and frequency range that is being utilized. So by changing the temperature or bandwidth, we can control the thermal noise. And also this thermal noise, we considered it as a white noise because it occurs at all frequencies. Let me explain this. This thermal noise depends on the bandwidth or the frequency change, but it does not depend on the frequency of that particular instrument, right? So it depends on the frequency bandwidth and independent of the frequency. Therefore, sometimes we can term it as a white noise because it is analog to the white light. I don't need you to get an idea in detail, but because this one is analog to white light, we can call this as the we can call this thermal noise as kind of white noise because it occurs at all frequencies. It is independent of frequency, but it depends on the bandwidth, right? And since this thermal noise depends on the temperature, we can easily reduce the noise by reducing temperature. We can minimize the temperature of each and every component. By reducing the temperature, we can reduce the thermal noise. And this thermal noise will be disappear at absolute zero. What is the absolute zero? What is the value of absolute zero? Absolute zero? Can one of you tell me what is the absolute zero? What is the temperature at absolute zero?
0 Kelvin.
0 Kelvin. Oh, yes, good. It is 0 Kelvin or minus 273 Celsius. But in practically, is it possible to reach absolute zero in practical situation?
No.
No, because 0 Kelvin or minus 273 Celsius, it's difficult for us to achieve. This thermal noise will be disappear only at absolute zero, but for us it's difficult to reach to absolute zero at our labs. Therefore, that means we cannot completely get rid of this thermal noise. What we can do, we can reduce the thermal noise only to a certain extent by reducing the temperature. Right? So that is the thermal noise. And the next one is the short noise. So short noise occurs when the electrons or other charged particles cross junctions. So the thermal noise arises because of the thermal agitation, and the short noise arises because of the crossing of these electrons or any other charged particles through junction. When it crosses through the junctions are like, we can say PN junctions, and it can be different materials. When the electrons pass through one type of material to other type of material, it's a junction. And when it pass through a vacuum from the air or whatever the solid material to vacuum, there is a junction. So this type of noise arises when the electrons move through the junctions, right? So due to the statistical variation of electrons across some junctions, so when the current or electrons flow through this junction, it can either this electrons or whatever the charged particle will be jump across the junction right away, or it will take some time for this electron jumping. Because of that, the flow rate of the electrons will be changing. Therefore, the current will be changing. When these changes happen, it will detect by the detector and the readout device as a short noise. And this one also considered as white noise, same as the thermal noise, because it is not depend on the frequencies. It occurs at all frequencies, right? That is short noise. And the flicker noise, the third one is the flicker noise. The flicker noise, the reasons for this flicker noise is it is not totally understood. So we cannot say like the thermal noise and the short noise. We cannot say certain any particular way why this flicker noise are there, and this flicker noise is frequency dependent. Both thermal noise and short noise are not frequency dependent, but the flicker noise is frequency dependent. Therefore, we cannot tell flicker noise as white noise since it is frequency dependent, right? And I told you it is frequency dependent, and the magnitude of this flicker noise is inversely proportional to frequency. That means 1 over f. Since it is inversely proportional to frequency, sometimes we refer this flicker noise as 1 over f noise. If you see somewhere 1 over f noise, it is same. It is the flicker noise. So it is significant at frequencies less than 100 Hertz. Why? The intensity, magnitude of the noise is inversely proportional to 1 over frequency, 1 over f. When the frequency is less, the magnitude of the noise is high. Since it is inversely proportional, when the frequency is getting lesser and lesser, the magnitude of the noise getting larger and larger. Therefore, when the frequencies are less than 100 Hertz, significant amount of flicker noise will be there in the signal. And one way to reduce this flicker noise is by using resistors that are wire wound or metallic film resistor. Most of the cases in instrument, these resistors are made out with carbon composition type. Instead of this carbon compositions, we can replace the resistors using wire wound or metallic film resistors. If we do that, we can reduce the amount of flicker noise. Right. The final type of the instrumental noise is environmental noise. Environmental noise, as the name implies, this noise is because of the environment. So, composite of different forms of noise that arise from the surrounding. So, this noise arises because of the lab environment. And what is happening there? Conductors in instrument pick up electromagnetic radiation and converting it to an electrical signal. So in any instrument, there are conductors. So these conductors pick up the electromagnetic radiation. Any change in the electromagnetic radiation associated with the environment. So there might be some TV, some sound, some any change in the electromagnetic radiation available in the lab environment will be picked up from the conductors in the instrument. Then this changes, because of these changes, again voltage fluctuations and current fluctuation will happen, and there will be some electrical signal. That electrical signal, which is due to the environmental change, that electrical signal will appear in the readout device as the noise. So this we call as the environmental noise. So this environmental noise can be eliminated. We can eliminate the source of the noise. Source is in the environment. We know what are the source. If there's a TV, we can, TV or radio, we can remove it. If there are some vibrating component, we can remove it. So we can completely remove it. We can eliminate the source. By eliminating the source, we can eliminate the noise. So that is the important thing in the environmental noise. We can completely get rid of this noise. But other noises, we cannot completely eliminate. We cannot completely get rid of the other types of noises, right? So how we can eliminate the environmental noise? If the instrument is in some noisy environment, if there are lots of disturbances, if there are lots of vibrations in the place which the instrument is kept, what we can do, simply we can move the instrument somewhere else. If we cannot make any changes to the environment, but we can move the instrument to somewhere else where there are no any environmental disturbances. And also we can isolate or condition the instrument power sources. That means sometimes instrument power sources, when it gets older, it will generate lots of noise, huge noise. You will hear them when we turn on the instrument. Sometimes much noise is there, and the vibrations. So what we can do here, either we can recondition the power sources, and also if there's a possibility, we can keep the power sources a little bit away from the instrument. So in that case also, we can get rid of this instrumental noise. And third one is the control in the temperature in the room. And control expansion, contraction of the components in the instrument. You might see that most of the time instrument rooms are air conditioned one. So we keep the instruments in a cool and dry place. So in that case, the reason for that, one reason is to control the temperature, right? By controlling the temperature, we can minimize, or we can eliminate some thermal expansion of the instrumental component. So that is one way to remove environmental noise. And as I said earlier, we can eliminate interferences by turning off radios or TVs, or we can remove these radios and TVs from the instrumental room. And another important thing is stray light or direct sunlight. Most of the cases, when we have the direct sunlight in the instrument, so it will change the signal. So the room should be away. We should keep the stray lights away from the open window. So it is better to have dark room, which does not have any stray lights or direct sunlight. Right? So that is the environmental noise. And so far we discussed the sources of noise. Any questions so far? I think it is a straightforward thing. So any questions so far? Okay, if not, we can move to the next section. But if you have any question, you can ask during the lecture, or you can type a message in chat box. Right. So we discuss what are the sources of noise. So okay, it may be a chemical or instrumental, and instrumental noises also can be classified into different types. And now since we know the sources, we should have an idea how to enhance the signal to noise ratio, right? The main thing is some noises we can eliminate, some noises we cannot eliminate, and there should be a way. Okay, someone has asked me whether I can give lecture notes. Actually, I didn't get chance to create Google Classroom, so I'll try to create Google Classroom this week, and then I will upload all the lecture materials, including the recordings, to the Google Classroom. So you will get an email once I create the Google Classroom, and then I will upload the lecture materials. Okay, right. All right. So now let's see how to enhance the signal to noise ratio. What are the methods available to enhance? So there are two types of methods, hardware method and software methods, to enhance the signal to noise ratio. Hardware, software. So the name suggests what it means. Hardware methods mean we can do any changes to the instrumental components, each and every components of the instrument. By changing the components, we can do some changes to signal to noise ratio. And also using some software or certain algorithms, we should be able to change the signal to noise ratio. Okay, the hardware methods. There are certain types of hardware methods. One is the grounding and shielding, analog filtering, and modulation. I will discuss this one in detail in next slide. And this hardware method, by using the hardware methods, we can remove or attenuate the noise without affecting the analytical signal significantly. When we change any hardware associated with the instrument, we can either remove or minimize or attenuate the noise. But here, it will not affect the signal. You will see sometimes when we use software method, it will cause certain alterations in the signal. But in the hardware methods, when we do hardware methods, the signal does not change significantly. But without changing the signal significantly, it will either remove or attenuate. We cannot say completely get rid of the signal all the time, but it will either attenuate or remove the noise. And software methods, these three types of methods are available: ensemble averaging, boxcar averaging, and digital filtering. You will learn these three in detail later in the upcoming slides also. So this is the main way, two main ways to enhance the signal to noise ratio. And for the software methods, we can use various types of computer algorithms. And what is happening there in the software methods, from the noisy data set, we can extract the signal with the minimum noise. So we are using different types of software or different types of computer algorithms we can extract the signal from the noisy data set. Right? So this is how let's discuss how we can do the signal noise ratio enhancement using these different methods. Okay. Grounding and shielding, that is one of the hardware method. Grounding and shielding. By grounding and shielding, environmental noise can be reduced. Environmental noise, you remember, that is one type of instrumental noise that can be reduced by grounding and shielding. Name says grounding and shielding. So we shield it and ground it. That means ground to some earth ground. So what is happening here? Surrounding a circuit or most critical conductor in the circuit with a conducting material that is attached to earth ground. So what we can do here, we cover a circuit, complete circuit, or if we cannot cover the complete circuit, we can cover the most crucial part or most critical conductor in the circuit. So we cover it with the conducting material, and then this conducting material can be earth ground. Right? When we do this one, grounding, shielding and grounding, then the conducting material that we covers, it acts as a shield, and that shield absorbs electromagnetic radiation from the surrounding. When some environmental change or environmental noise is there, it generates some electromagnetic radiation. Then what is normally happen, that electromagnetic radiation will be absorbed by the conductor of the instrument. So instead, before it goes to the conductors in the circuit, this shield will absorb the electromagnetic radiation. When it absorbs the electromagnetic radiation, since now the shield has been grounded, now it will not go to the instrument. Instead, it will be ground. Right? So that is what happens in this way, in this hardware method, grounding and shielding. Sorry. So by grounding and shielding, then we can eliminate the signal. We can eliminate the noise part. So environmental noise part can be removed from the signal. Therefore, when the noise is decreasing, signal to noise ratio is increasing. Therefore, the signal, intensity of the signal will be increased. So we will get a nice peak at the end. Right? So that is one way to enhance the signal to noise ratio. Another way is analog filtering. Again, how this happens, I don't expect from you to have much idea about how it happens, but instead you can roughly get an idea what is happening there. And analog filtering, there are different ways, different filters, low pass filters, notch filters, like that. So we can incorporate this here. This figure shows incorporating low pass filter to remove the higher frequency portion of signal. So what is happening here? This is the noise signal. Initially you will see a signal like this, right? So the noise signal, this peak, I don't know if it is visible. I hope you can clearly see this peak and peak here are the interested peak, but it is difficult for us to distinguish the peak from the noise because the noise is high in this spectrum. Right. Therefore, what we can do, we will do some low pass filtering, and here the signal will be multiplied by some filter function. I will not go into detail here, and it will multiply by a filter function, and after that multiplication you will see a signal, and then the final output. You can see now after adding this low pass filter, we can clearly get a nice sharp peaks without signal. Right, that is one way for analog filtering. It's a hardware method. And notch filter, it removes interfering frequency. So at the very beginning, it doesn't show nice peak, and it has some fluctuating intensities. So entire signal has interferences, and in that case also signal will be multiplied by some filter function, and then we will get, at the end we will get a nice sharp and clear peak. Right, so these are two different methods, two different hardware methods available for two different analog filtering methods available to do the enhance the signal to noise ratio. And third type of the hardware method is modulation. The modulation, I will tell you an example. This is the one way of reducing noise in the atomic absorption spectrophotometer. So the atomic absorption flame, when the light passes through it, and it will go through a noisy detector. Because of that noisy detector, it will give a noisy signal. So there's one way of modulating. We can have a chopper in between the flame and the detector. Right? So this is a kind of rotating thing, and when it rotates, it will cut certain part of the light, and it will allow certain parts to go through the detector. Because you can imagine, suppose these are open sides, these two clears, suppose it is a circular thing, and it's a circle, and there are two openings like this, and these are some hard material, light cannot pass through this. Now when this chopper rotates, what is happening? When it rotates, certain part of light will go through the chopper, but certain part will chop. It will not go through the chopper. Right? So then it will go to the detector, and this is the modulated signal. This chopper will act as a modulator, and it will chop the light path. It will chop the light path, and what will happen, since it chopped the light path, signal will appear at the chopper frequency when it rotates. And then when the light goes through the detector, we will see the modulated signal. Now you can see, we can, by modulating the signal, we can get a better signal compared to the noisy signal. So that modulation, this chopping is one method of modulation. And there's another way to modulate radio, especially the radio signal. So modulation of radio signal is another example. Amplitude modulation, AM. Here what is happening? High frequency carrier signal will be used, and the signal, the normal audio signal will be multiplied by this high frequency carrier signal, and it will generate the modulated signal. So by using that high frequency carrier signal, by multiplying using a high frequency carrier signal, we can modulate the signal and get high intense signal compared to the initial one with lesser amount of noise. So those are two examples of the modulation. And let's discuss ensemble averaging. So this is a software method. And this is one of the mostly used method. You know that most of the cases, when we, for example, let's take UV, we are running some UV visible analysis, okay? So that is the most easiest thing, and all of us have done it. So when we do the UV visible analysis, what is the best way? Tell me. I will say like this. I will take, what is the normal way? How many spectra you acquire? How many spectral acquisition normally you do? When you do the UV analysis, I think you have done it. So how many spectral analysis you did? Have you used the UV visible spectrophotometer in the instrument room before? In the second year experiments? No? Yes or no? Can you hear me? No answer.
Yes, madam.
You have used. Okay. So can you remember when you take the spectrum, normally how many spectra you took? How many scans? Let's say how many scans you did? If you remember, I don't know whether you remember it. If you don't remember, that's okay. If you remember, tell me.
To get lambda max, one scan.
Okay. You got only one scan to get lambda max. Okay. So that's fine. But normally you will do research in next year, in the fourth year. So remember, even you use UV spectral analysis, and you know when we do the titration or whatever, yeah, let's say titration, we normally do 3 replicates, right? Just to increase the accuracy. Similarly, when we do spectral analysis also, we will do at least 3 scans, and we will take the average. We don't need to do averaging manually. The instrument will automatically will give the average spectra. What we do at the very beginning, we have to set some methods. When we set in the methods, we put, it will ask how many scans. So we can say 3 or 10 or whatever the number of scans. And most of the cases, if the signal is, even if we can get a good signal, we usually get 3 scans and get the average. And that is kind of ensemble averaging. That's why I need to get that example, because UV, we all are familiar with the UV, and we take 3 or more spectrum, and computer will average those spectra for us, And at the end, what we will get the average spectrum. So it is kind of ensemble averaging. So it is the software methods available. So what is happening here? First, we collect multiple signals over the same time or wavelength domain. It can be within a time domain or wavelength domain. We collect the multiple signals over wavelength or time domain and then calculate the mean signal at each point in the domain. Basically, we get the mean of all multiple signals and then replot the averaged signal. That is the final signal. And since the noise is random, noise can be either plus or minus. Since the noise is random, this helps reduce the overall noise by cancellation. So when the noise is random, it can be either plus or minus. When it is random, it will help to reduce the overall noise. So look at the diagram, look at the image shown here. Here, the first graph shows the digital data before processing by ensemble averaging. This is all the data acquired before averaging. First spectrum, second spectrum, third and fourth. We will be able to take a different spectra. Then what is doing during the ensemble average, for first data point, let's say at this wavelength, we average all 4 values at this wavelength. And then by averaging, we replot this. We replot the average signal by putting the average signal here. And similarly, we will do the ensemble averaging for all the data points and we will get the average spectrum. You see, this spectrum, individual spectrum, it does not have nice shape. And it's because of the reason, one reason is it's associated with noise. But by averaging, we will end up with a nice, smooth curve. So the average spectrum is a ensemble average. We did the ensemble average here and we will be able to get a nice and smooth spectrum here. So that is the ensemble averaging. And look at here. When we do the one scan, it's really difficult to distinguish signal, any important signal here. But when we increase the number of scans to 50, now we can see some sharp peaks. So 50 scans are better than the single scan. But when we even increase the number of scans to 200, now we can get really nice sharp peaks in our spectrum. So here we have done the ensemble averaging. So normally when we do the UV, NMR or whatever the spectroscopic method, we increase the number of scans. When we increase the number of scans, we will get a nice signal. You will, when you do the practical or when you do the research, you will find it by yourself. So we will not get nice peaks. Most of the cases we will not get nice peak. So when we do some lab work, some elementary laboratory work, we will get nice peaks because we will get a much less matrix effect and much less noise and intense. We will get intense peak. But whenever you do research, you will not be able to get nice peak most of the cases. So very first thing you have to do, if the we call it as resolution, the spectral resolution is poor. The first one has really poor spectral resolution. So in order to enhance the spectral resolution, the very first thing we normally do is we will increase the number of scans, right? So by increasing the number of scans, we can get nice spectral features. So that is kind of ensemble averaging. All right, now let's move to boxcar averaging. It's another type of software method, boxcar averaging. What is happening here? Here, first we take an average of 2 or more signals in some domain. So, look at the graph. We have one spectrum here, the boxcar one. What we have done here, we take the average of the signal 1, 2, 3. We took the first, second, and third data points, and the average of the first 3 data points has been taken, and that average has been plotted here. This is the boxcar 1. Boxcar 1 means the average of the first 3 data set, right? Take the average of 2 or more signals in some domain. Plot these points as the average signal in the same domain. Take the average 2 or more signal and plot it as the average signal in the same domain. And same thing will be done for the second data set. First 3 set, we took the average and plot it. And second 3, 4, 5, and 6 one, we take the average of these 3 and plot it here. Similarly, do the averaging of all the data points throughout the spectrum and replot it in another graph, but the domains should be same. So this is the original spectrum, and you will get a spectrum after boxcar averaging. Spectrum will be looks like this. Here also you can see the peak is smooth than the previous one, than the original. We will get a smooth, nice peak after boxcar averaging. And also in the ensemble averaging, you have to take 3 or more spectrum. Ensemble averaging is not possible with one spectrum, but this boxcar averaging is possible with one spectrum. So it can be done with just one set of data, right? And here, when we do, unlike in the ensemble averaging, when we do the boxcar averaging, it will lose some details in the overall signal. So you will see the peak shape also little bit different. And since we are averaging 2 or 3 consecutive data sets, it will cause some loss of the details. So that is one of the disadvantage in this boxcar averaging method. So overall signal, when we get the overall signal, it will lose some details in the original one. So, but still we can do this one because still we will be able to extract important information than from the original one. So that is how we can perform boxcar averaging. Okay, so we have discussed how to enhance the signal. Those are the methods how we can enhance signal to noise ratio. So far we discussed what are the signals and noise and the sources and how to enhance signal to noise ratio. Any question from this? This is most of the time, this entire thing is theory. We don't have any calculation or anything. So theory part is there. You will, I highly encourage you and I highly recommend you, please read the Advanced Analytical Chemistry textbook, the school one. So it will give lots of information, but most of the information you do not need at this level. But for your knowledge, it will be better you go through that book. So this lecture series has been taken from that book. I refer that as the textbook here. Any question? If you don't have any question, we can move to the next section. Okay, shall we move then? All right.
Okay, ma'am.
I will stop sharing this and then go to the next one. Okay, can you see new presentation? Is it visible?
Yes, ma'am.
Okay, thank you. All right, so now we are coming to the main part, spectroscopic method. So we learned the basic of the instrumentation and the noise and signals, all these things, and how to select an instrumental method. And then next thing we have to discuss is the spectroscopic method. So that will be the most important thing. You will learn different types of spectroscopic methods. I know you know some of these techniques already. And also in the Advanced Analytical Chemistry 1, the rest of the course, as well as in the Advanced Analytical Chemistry 2 course unit, you will learn the more details of the spectroscopic methods. So, but when you learn it, you will learn the basic of that particular instrument. But here, what I am going to do is the main and the basic things which you should know when you follow the spectroscopic methods. So we will discuss basic principles and main optical components and what are the common optical components in these spectrophotometric methods, right? Okay. So introduction to spectroscopic method. Right, spectroscopy. You know the spectroscopy. Most of the time you heard the word spectroscopy, spectrophotometer, and all these things. So what does spectroscopy mean? So that is the science, or that is the study that deals with the interactions of various types of radiation with matter. During the spectroscopy, we will learn how the radiation will interact with matter, how the various types of radiation interacts with the matter. So that is the definition for spectroscopy, right? And when it comes to spectrometry or spectrometric method, these are two different terms, spectroscopy and spectrometric method. Even though we don't pay much attention, we think it's same, but definition wise, these are two different terms. Spectroscopy is the interaction. What are the interaction? And in the spectroscopic method, we measure. Actually, we measure. So the measurement of the intensity of radiation with a phototransducer or other type of electronic device. In the spectroscopy, we deal or analyze or study the interactions of various types of radiation with matter. But when it comes to the spectrometric method, actually we measure the intensity of the radiation. How we measure it? With a photoelectric transducer or any other type of electronic device. Right? And also, in the definition I told, it is interaction of the various type of radiation with matter. But this spectroscopy term, we also extend it to techniques with, we call mass spectroscopy, electron spectroscopy, right? So in mass and electron spectroscopy, there's no radiation, but there we use the ions or electrons. But in that case also, the spectroscopy term has been extended to those techniques which are dealing with ions or electrons, such as mass or electron spectroscopy. Right? So that is the definition of the spectroscopy. And we know that electromagnetic radiation, we will abbreviate as EMR. If in upcoming slides it says EMR, it's for the electromagnetic radiation. So electromagnetic radiations are the main thing, or the radiation involved in the spectroscopy, right? Or the spectroscopic methods. So what is this electromagnetic radiation? What does that mean? This electromagnetic radiation, it is a form of energy. It has both wave and particle properties. I think you heard, not I think, you should heard about wave particle duality. You already know the wave particle duality. This electromagnetic radiation has wave nature as well as particle nature, right? So the energy of this electromagnetic radiation we can call as it has wave particle duality. How wave nature, how we can say it has wave nature? Many properties can be described by classical sinusoidal wave model. You know that sigma sine wave shaped wave model. You learned that the sine shaped wave model. So many properties in electromagnetic radiation can be described using this classical wave model. It has sinusoidal shape or sine wave shape, and therefore we call this as a wave nature. Electromagnetic radiations has wavelength, frequency, velocity, amplitude. All those things are present in the wave model. Therefore, this EMR or electromagnetic radiation have wave nature, and they can pass through the vacuum, and this electromagnetic radiation can absorb and emit radiant energy. you know that in absorption when we talk about the absorption spectroscopy, it can absorb radiation, and also in the fluorescence it can emit radiation. So in both these techniques, electromagnetic radiations are associated with. So instead of wave nature, if it only has wave nature, it cannot absorb or emission. But this EMR can absorb and emit radiant energy. This means this electromagnetic radiation has particle nature. And you might know, you should know that you have heard about the quantum packets, and because of this part, we can explain this particle nature using that quantum mechanics. The wavelength, the radiations are associated with the quantum packets. So likewise, we can say that there's a wave-particle duality of the electromagnetic radiation. Right. Now let's see this electromagnetic radiation as a wave, how it acts as a wave. So suppose the x direction is the direction of propagation. This is the direction of propagation of the electromagnetic radiation. And perpendicular to this propagation direction, it has an electric field. Right? It has an electric field like this. It is perpendicular to direction of propagation. And then again perpendicular to the both propagation direction as well as to the electric field, there's a magnetic field. So since it has electric and magnetic field, we call it as electromagnetic radiation. This radiation has both electric as well as magnetic field. So this is how it acts as a wave. And I mentioned to you earlier that this has wavelength, amplitude, and all these things, and it is similar to the sine wave shape of the wave. This is the 2D image of the electric field shown here. If we talk about the electric field, and here I showed you the 2D image of the electric field. So now let's see what are the properties of this electromagnetic radiation. Same as the wave, it has period. So the period means the time in seconds which required for one cycle to pass a fixed point in space. Period, you know that hour there or something, period, right? And the frequency. And the frequency, the symbol is nu. I apologize here, I couldn't find the correct symbol. This is the one. Actually, this should be other way, right? The nu should be, I know you already know how to write nu. But before I upload the material, I will find whether I can get a correct frequency symbol. This should be other way, right? But in the symbols, I couldn't find the correct symbol. It gives, instead of nu, it gives the V type of thing. But there should be a I wish I can write it, but keep in mind the frequency symbol. You should know the correct one. It's similar to the other mirror image of this one, right? Correct frequency when you write. Make sure don't use V, use that nu. Frequency, the number of cycles which pass a fixed point in space per second. So that is the frequency, number of cycles pass in a point per second. Those are the normal definitions of the wave. It is applicable for the electromagnetic radiation as well. And the amplitude is the maximum length of the electric vector in the wave or the maximum height of a wave. Amplitude, maximum length or height of the electric vector in the wave. And the wavelength is the distance between two identical adjacent points. So it can be either two adjacent maxima or two adjacent minima. And the wave number is the number of waves per centimeter. The units of wave number is in per centimeter and 1 over lambda. I discussed all these definitions, especially wave numbers and wavelength. Wave number, you will familiar with, you are familiar with the wave number, because in the IR, most of the cases we use wave number, and in other spectroscopic method we use wavelength. So wave number is the 1 over lambda. And another thing, most of the time I have seen when people write wavelength, they write it as two different two words. Wavelength is not a two word, it's a single word. Remember, when you write anything or when you write or type, wavelength is a single word. It's not a two words, right? So this wavelength, wave numbers, you will learn throughout the spectroscopic section. Whatever the spectroscopic method you learn, you will learn this too, and as well as frequency and velocity of propagation. When the electromagnetic radiation propagate, we can calculate the velocity. Velocity, same as the speed, but it's a different. Velocity means the directional one, and speed of, we can call it as speed of light equals to the frequency times wavelength, right? That is the equation to find the speed of light. And the frequency of a beam of radiation is determined by the source. Frequency is determined by the source. And velocity of radiation depends on the composition of the medium through which it passes. And frequency, or mu, is determined by the source of the radiation. And the velocity depends on the composition of the medium. So depending on the composition of the medium, the velocity can be changed. And in a vacuum, for electromagnetic radiation, the speed in vacuum is a constant. You know this number also. The speed in the vacuum is 2.99792 times 10 to the power 8 meters per second. That is the speed of light. Well, speed of light or speed of electromagnetic radiation in a vacuum. And when it comes to the air, speed of light in air is only 0.03% less than the one in the vacuum. So it is 0.03% less than the vacuum. And if we round off those numbers to let's say to 3 figures, we can get 3.00. That is the normal value we use when we do the calculation. We use this number 3.00 times 10 to the power 8. So for both air and vacuum, we can use this one because the difference is really small. But keep in mind, actually, the speed of light is not identical in air and vacuum. It has a little bit different, but there's no significant difference. Therefore, we can use the same value for the speed of light in the air and vacuum. Right. Okay. Now let's see what is happening when the light wave pass through different medium. So suppose the light wave pass through air and then again glass medium and again air. And the source is same, right? Because the source is same, the frequency remains same. Frequency will not be changed in different medium. But the wavelength has been changed. Therefore, velocity is changed. For example, think like this way. So, you are traveling through a certain road, or let's say through a certain road, and when there's less traffic, we can move easily or we can go faster. But when there are a lot of traffic, it is difficult for us to ride faster. So automatically we have to slow down. Same as here. Now when we go through the air or vacuum, there are less interferences, and the light wave can go through air or vacuum very easily. But when we consider the glass, there are some electrons in the glass materials. So this light will interact with those surface electrons, and then because of this interaction of the radiation with the matter or radiation with the electrons, then the speed or velocity will become less, so it will be changed, and it will be, therefore the wavelength will be changed and velocity will be changed, but the source, since the source is same, the frequency will not be changed, right? That is what happens when the light wave pass through different mediums. I think it's clear. So frequency remains same, velocity and wavelength change. Next, Planck's equation. And you learned that one earlier also. So Planck's equation and Planck's constant. So Max Planck developed this one. E equals h nu, and from this equation, C equals nu lambda. Normally, if it is a vacuum, it is 3.10 to the power 8. This is the value we will use in most cases, in most of the time, if it is not specifically measured. So the C we can consider it as a constant if it is not specifically mentioned, right? And we can rearrange this equation, the C equals h nu to nu equals C over lambda, and by substituting the new value, the frequency values to the Planck's equation, we will get C equals hc over lambda, and E equals hc over lambda means the C over lambda is nu, C over lambda is nu, and E equals hc nu. And this equation is important when you learn different spectroscopic techniques. So that is the one of the equations. For example, if I tell the let's say IR, when you learn the IR spectroscopy, So you will learn the relationship between the wave number and reduced mass and all the constants. So in that case, you have to know this Planck's equation. You have to know that the basis is the Planck's equation. And using the Planck's equation, you should know how to get the relationship between the frequency and energy and wavelength and energy. All these things, the derivation, you should be familiar. Right. Now let's see the electromagnetic spectrum. So this electromagnetic spectrum can be represented in either in the vertical way or horizontal way. The image that I took is this one, but there's another image, I will show it later. And here, sorry, this is the electromagnetic spectrum. So you see frequency values are here, and this is the wavelength. I'm sorry, the label is missing here. This is the wavelength values, right? This is the frequency scale. And when the frequency is high, so if we go to the frequency scale, this is the lower, the bottom is the lowest number, and from bottom to top, the frequency is increasing. Bottom is 10 to the power 5, top is 10 to the power 21. So when we go from bottom to top, the frequency is increasing, and this scale is the wavelength, and in the top it is 10 to the power minus 12, bottom is 10 to the power 3, and when we go from bottom to top, the wavelength is decreasing, right? And higher the frequency, shorter the wavelength. When the frequency is highest, wavelength is lowest. When the frequency is lowest, wavelength is highest. Therefore, wavelength and frequency has inverse relationship. So there's an inverse proportionality between the wavelength and frequency. And based on the wavelength or frequency values, you will see the different types of electromagnetic radiation. The gamma rays, X-rays, UV, visible, near IR, mid IR, far IR, microwave and radio frequency. And the visible spectrum also, the wavelength from 400 to 700, from UV to, from violet to red. And I think I would recommend you to remember these numbers. Especially the visible spectrum, the wavelength region, you should know this. You should remember. And not the exact value, 400 violet, 800 or 700 red. And this is in between numbers also. And you should remember these wavelength values associated with the colors. And also the X-ray rough, you don't need to have a clear idea, but you should have the rough idea of this wavelength values and the type of radiation. right? I would say keep in mind the wavelength region is easy than the frequency, because once you know the wavelength, you can calculate the frequency if necessary. I would recommend to remember the wavelength values, right? And the order, gamma rays to radio frequency, how the order changed, definitely you should remember that. Gamma, X, UV, Vis, near IR, mid IR, phi IR. So at least gamma has the lowest wavelength and the radio has the highest wavelength. You should remember the order, right? So if you were asked to write the electromagnetic spectrum, you should know how to write it, right? And here, this is another way to represent the electromagnetic spectrum, gamma to radio wave, and some are overlapping here. So the same electromagnetic spectrum here, instead of vertical, here I put it as a horizontal. So either way is fine. Whatever the easiest way or whatever the convenient way you can remember. So, but both are same. Sometimes in certain books the numbers will have little variation. So no need to worry about that one. But you can have the rough idea of the wavelength values. Okay. So this is another way to represent electromagnetic spectrum. So you will see some gamma, X-ray, UV, visible, all these things, microwave, all these radiations associate with different spectroscopic methods, right? All right. Then let's see some of the common spectroscopic methods based on electromagnetic radiation. And this table summarizes the common spectroscopic method associated with the different types of electromagnetic radiation. So UV visible, let's start from that one, because we all know this UV visible very well. And UV visible, absorption, emission, and fluorescence all associate with this wavelength range. And normally when you do a UV scan, we will select 200 to 800 as the wavelength scan range. So it's because the wavelength range, electromagnetic wavelength range is, which is correspond to the UV vis, is this value 180 to 780. I don't want you to remember this wave number range, because it is difficult to remember lots of things. So whenever you know the wavelength range, we can calculate either frequency, wave number, or whatever the thing. So one is enough. No need to remember all these things. But it is worth it to remember at least wavelength range. So in the UV vis, we know all the quantum transitions is bonding electron transition. We can see the electron transition, bonding electron transitions in the UV vis. And when it comes to the IR and Raman, IR is absorption one, Raman scattering. We will discuss this in detail. And IR and Raman is associated with the rotation or vibration of the molecule. Right? And the microwave. So IR absorption spectrophotometer is within the IR region, and the microwave absorption is in the microwave region, and it is associated with the rotation of molecules, and same as the electron spin, nuclear magnetic resonance associated with the spin of the electrons and spin-off nuclei. And if we go away from the UV in the top part, from the UVs to, we can have vacuum UV. So in wavelength region is only the UV range. It also associates with bonding electron. And X-ray. X-ray can be the absorption, X-ray absorption, emission, fluorescence, or diffraction. All are associated with the inner electron transition. You know, during the X-ray, electrons in the inner core will transfer, therefore it involves with the inner electron transition. And the gamma ray is the nuclear. So this is the summary of the common spectroscopic methods available, right? So I will stop today from this point, and any questions from today's lecture or from this part? So I just give you a brief introduction, because we can talk in more details about the optical spectroscopy component in next lecture. So as a basic, I just want to give you an idea about the electromagnetic radiation. So any questions so far? Yeah, seems like no question. And can you please send your index numbers to chat box? I need to get the attendance. Please send your index number. Then I can take attendance from that one. Okay, what we can do, if you don't have question, we can stop here. So what you can do, if you finish sending that your index number, you can leave the meeting. Then once you all leave the meeting, I can close it. So then have a nice day. Please leave the meeting if you already finished sending your index numbers.
Thank you, madam.
Okay, you're welcome.
Thank you, madam.
You're welcome. So, Dulaj, have you sent your index number? Dulaj, are you there? And Jayaratna.
Yes, madam.
Okay, have you sent your index number?
Yes, madam. I send it.
Okay, then can you leave the meeting? Because
Yes.
then I will lose some And you and Dulaj only. Dulaj, have you sent your index number? Dulaj.